So today we're going to cover blood. We're not going to get covered in blood because that'd be gross, but we're going to cover blood. We're going to talk about the components of blood. We're going to talk about how there's liquid and solid portions of blood. We're going to talk about the difference between red blood cells and white blood cells and what they do and how many there are and what their jobs are and how long they last for. And if we have time, we will also cover blood types, but I'm okay with covering that tomorrow in class. So we'll get started on blood. So the composition of blood is such that it's separated into two categories. The first category are called formed elements, or is called formed elements. And formed elements consist of cells and platelets. The cells that are formed elements, you can kind of think of these as like solid portion of blood, are white blood cells and red blood cells. And platelets are little fragments, broken off pieces of really big cells. The other portion of blood is the liquid portion, which is plasma. And as it says there, plasma is the liquid portion of blood. So formed elements, white blood cells, red blood cells, and platelets. The liquid portion is plasma. So you may think of your blood as being entirely just liquid, but there's little parts of it that obviously are solid portions within there. It's like a solution. We good there, folks? Okay. On this big slide, there's a lot of info, but really what I'm going to focus on here for you is the left side. So I'm going to take this marker and cut it off sort of there for now. So we're going to pay attention to stuff on the left. You don't need to make that big squiggly line. But some things to pay attention to here are the red blood cells, which are right here. So the red blood cells are known as erythrocytes. That's a fancy scientific name where the prefix erythro means it relates to red blood cells. In terms of number, there are 4 to 6 million per cubic millimeter of blood. Cubic millimeter is like 1 millimeter by 1 millimeter by 1 millimeter, like that. Tiny. There are 4 to 6 million red blood cells in there. Next, there are white blood cells, and I do have a white pen, but it's not going to show through, so I'll do a black pen. White blood cells encompass this column as well as the middle portion. So there are, and it's separated into 2 types. The first type are granular leukocytes, which are these ones. And the second type are agranular leukocytes, which are these ones. Now, in grade 7, maybe, grade 5 or 7, you learned about the difference between biotic and abiotic, meaning living and non-living things. So granular and agranular basically means there are some granules in one and there are some without granules. So the ones that do have granules or little grains are neutrophils, eosinophils, and basophils. And you can even see by the image there, they have little speckles, little grains, and those are granular leukocytes. On the other hand, you do have 2 types of agranular leukocytes, which are lymphocytes and monocytes here in the middle of the page. These ones do not have a speckly exterior or interior, so they are agranular. They are without grains or granules. Oop, I made a little mistake here. This little portion here, platelets, is on its own. That's not part of the white blood cells, but we will talk about those later. Now, while red blood cells are called erythrocytes, white blood cells are called leukocytes, which on the far left I'm underlining. And platelets are called thrombocytes. This is all a lead-in into what we're talking about today in class. So thrombocytes in the middle bottom portion of the page. So that's more of a visual representation. There is one last thing I want to talk about here on this page, and that is this right here. Shows up 3 times. This is a test tube filled with blood that has been centrifuged, which a centrifuge means it's a machine that spins really quickly in a circle, high RPMs, rotations per minute, like really fast. And what that does is it actually separates the components of blood. So this is what's called centrifuged blood.
Do they use that a lot in like labs and stuff?
Yeah, they do it. I'll use it a lot in labs. So centrifuged blood. Now you'll see that above this little white strip here, all the way down to the bottom, that is called formed elements. That's red blood cells, white blood cells, platelets. And then in the top portion, that's the plasma, and that's the liquid portion of blood. Notice that the liquid portion is 55%, so it's a majority liquid, while the formed elements are 45%. It's close to 50-50, but it is considered a liquid just because of that. Any questions? There's a lot of info on that page. Okay, I'm going to clear my drawings. Yes, Fallon.
Are we going to need to know which type, like the 3 types of, and then 2 types for A?
Good question. Are we going to need to know the 3 types of granular leukocytes, 2 types of agranular leukocytes? Yes, but sorry? You will need to know detail on them, but we're going to take some notes on them today. This is basically a big lead-in into today's notes. Seth, question.
So, like, is plasma always going to be more than, like, there, like, say, is there going to be more plasma than there is blood, or, like, all the time?
Well, plasma is a part of blood, so.
Yeah, like, say, like, because this is, like, 55% plasma, right?
Right.
Is that, like, just blood in general is 55% plasma, or?
Yes.
Okay.
It will always be a majority plasma.
Okay.
Otherwise, your blood will not be, if it was a majority formed elements, your blood would not flow.
Okay.
Because it would no longer be a liquid, it'd be majority solid, and then it would be like sludge. Good question. Okay, moving on. Plasma. So plasma, as we know, is the liquid portion of blood. It's composed of these little proteins called plasma proteins, which maintain your blood's volume by contributing to osmotic pressure. And what that means is it relates to the pressure, the water pressure of your blood. Okay, we're going to go through some examples of plasma proteins. The first one is called fibrinogen, and we will talk about fibrinogen in today's class as well. So that relates to blood clotting. There are also plasma proteins called immunoglobulins. That's a long word. 6 syllables, immunoglobulins. Back in October when we covered this unit, I made a really, really bad joke about how if you go trick-or-treating, you might go around and see some immunoglobulins instead of immunoglobulins. It was really bad. I'm getting like sympathy Snickers in class here. Anyway, because of the prefix immuno, it relates to immune system or immunity, keeping you healthy. There are also plasma proteins called albumins, which help with transporting things through your bloodstream, and many, many others. Lastly, there are organic and inorganic substances that are in your plasma, and that's like things like your gases in your blood that dissolve in them, like oxygen, as well as carbon dioxide. So that space is blood gases. Yeah, question.
It's true that yawning slows down your heart rate.
Question was, is it true that yawning slows down your heart rate? I do not know. If we try to break that down, yawning would mean an increase in oxygen that goes through your lungs. It's a larger intake of oxygen, which means more oxygen possibly in your bloodstream that gets diffused in at your lungs, which means you get more oxygen flowing around to your systemic bloodstream, which means your heart doesn't have to pump as hard. So I guess technically that makes sense. Maybe. All right, moving on to the next slide on the next page, which is red blood cells. Red blood cells, any idea where they're made? That's correct, Jack. Thank you for raising your hand, Fallon. Bone marrow is correct. So you've done your reading. They are made in your red bone marrow. And in terms of number, we've talked about that, 4 to 6 million per cubic millimeter of blood. That is a lot. Now, they do have a nucleus when they're freshly made. I'm talking about them like they're donuts, which is hilarious. But then as they mature, they lose their nucleus. So you guys know what a nucleus is in a cell. I'm going to draw what a red blood cell looks like. So if I'm drawing it sort of on an angle, kind of looks like this. And then it's got a little dimple or a flat inside, which relates to, if you took a look at it from the side, it would look like this. So there's actually like a depression on both the top and bottom, or a cave, a curve almost. And that's because it's called a biconcave disc. It's got two sort of curved sides. It's biconcave. And that allows for greater surface area to carry oxygen. It's like a donut. There's our second donut reference. It's like a donut without the hole. It's like a flat center of a donut. Hudson Vanderberg just asked, what if the Earth is a donut? I just feel like it's right to actually say what people ask in class, so that people at home know.
They didn't believe that. Yeah, we got supported. It's the new theory.
Say the Earth is a donut?
Everything's a donut.
Everything's a donut.
We're all in just a donut. And like reality, as we know it, is what it is.
All right, Hudson, let's get back to this. By the way, I can make some of you hum a song or think of a song just by saying 3 words. Everything is awesome.
Oh my God, no.
Hudson is now singing, everybody, just to let you know. Moving on. And you know what? I record these lessons, so that's awesome. Red blood cells contain something called hemoglobin, which is what carries oxygen. It's the thing that oxygen binds to. And more specifically, there's a portion of hemoglobin called the heme portion that oxygen binds to. Hemoglobin is red, and that's where red blood cells get their red color from iron. And as I'd said, there's a heme portion that binds to oxygen. And there are 4 binding sites for oxygen, 4 heme molecules that oxygen will bind to. In terms of amount of oxygen per milliliter of blood, there are 20 milliliters of oxygen. So 20% of blood is carries oxygen. And then there's a note there about carbon monoxide. I'll give you a few seconds to write that down before I explain that. Okay, getting to carbon monoxide. Carbon monoxide, you probably heard about carbon monoxide being very dangerous because it's odorless, colorless gas. And the reason that carbon monoxide is dangerous is because when there's no oxygen around, or if there's an abundance of carbon monoxide can actually bind to those heme sites in place of oxygen. Now, if you follow along with this and follow the path of it, if you breathe in carbon monoxide, it diffuses into your bloodstream at your lungs. It gets picked up by the red blood cells, and then it gets sent to your heart, which the heart, as you already know, pumps that oxygenated blood, which is not really doesn't have oxygen. It's got carbon monoxide rich blood to your whole body. And then it goes to the capillaries and exchanges, instead of oxygen for carbon dioxide, it's exchanging carbon monoxide for carbon dioxide. At which point your tissues and your cells say, thanks for this, but I don't know what to do with this because our body, my cells, your cell's components can't actually use carbon monoxide. So it's actually toxic to it. So then the cells try to use it, it fails, and the cells start to break down and die. And as you know, from living things are organized, cells start to break down, tissues start to break down, organs start to fail, organ systems fail, and then it could be very dangerous and be fatal if there's a large amount of carbon monoxide that gets inhaled over oxygen. So that's why carbon monoxide is very dangerous. I'm going to clear my drawings here so we can move on to the next slide, which is a drawing, no, a diagram, sorry, that looks like this. So I'm going to do some drawing here. If I can find my cursor, there we go. Let's use this color blue. So on the left side of the screen, you'll see a very zoomed in image which has capillaries, and I'm outlining the capillaries here in blue, sort of a Y shape, and then they filter down. You'll notice that, as we've mentioned previously, the width of a capillary is one cell wide, which is true because there's one red blood cell, there's another one, there's another one, there's another one, here are some other ones, and that allows for exchange of oxygen for carbon dioxide. On the right side, we're zooming into a red blood cell, and there again is the sort of dip in the middle. Circle, 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 the flat portion, the biconcave disc portion of the red blood cell. Now, on the right side, you'll see there's the little red bits, those are iron. And then each of these little sort of yellow portions, those are the heme groups. There's one there as well. There's one on the bottom left and one on the bottom right. So as I'd said before, there are 4 binding sites for oxygen. And this whole thing itself is a hemoglobin molecule. No questions about that? Okay, so I'll clear my drawings, 4 binding sites for oxygen at each one of those little yellow bits there. We're now going to talk about a little bit more about red blood cells and how long they live. Any guesses for how long a red blood cell lives for? Not 100 years. Not a day.
3 days. Isn't it shorter?
Not 3 days.
Oh.
It is 120 days, which is about 4 months.
Wow.
So they survive for about 4 months. And then at that point, they are destroyed in the liver, and your body is very efficient in reusing and recycling stuff that it can reuse and recycle. So the hemoglobin is broken down, The iron is recycled and taken back to the bone marrow to create more red blood cells. The heme portion is the only thing that it can't be reused, or cannot be reused. So it's broken down or degraded and then excreted as bile pigments. And where is it excreted? It's excreted in your feces or your poop or your stool. So that's the one thing that your body does get rid of. Has anybody heard of anemia before? So anemia is usually low iron in your body caused by a decrease of blood cells, decrease of red blood cells. And the most common type comes from iron deficiency. I had a student at my old school who was anemic, diagnosed as anemic, and the recommendation from her doctor was first these little pills that had ground up like not iron itself, but it had iron in them, so iron pills. And girls, if you end up down the road becoming pregnant, your doctor may recommend that you take iron pills, just because you start to lose iron during pregnancy. Okay, so the student, she either had to take these iron pills, or the doctor said another thing you could do is cook up some liver at home, put it into a blender with water, and make into a liver smoothie or milkshake. Not milkshake because there's no milk, which sounds gross, because if you've ever eaten liver, it's sort of got a different consistency. It's sort of, bitter, grainy, but it's really high in iron. Okay, so red blood cells are made and stimulated by this hormone called erythropoietin. And if you end up going into anything medical field related, erythropoietins, also known as EPO. And erythropoietin is a hormone that's made in the kidneys, and the kidneys start to produce more EPO when your body has low oxygen. So it's like, oh, your body has low oxygen in the blood. I need to make more red blood cells so we can carry more oxygen in the blood. So that's done by the kidneys. Okay, moving on. We're going to get to white blood cells now. But a quick review, quick summary of red blood cells. How long do they live for? 120 days. What's their shape? They're round, but right, the indent, so that's a biconcave disc. What's their job? Bring oxygen, carry oxygen throughout the body. Good. And there's another question that I forget. How many of them are there?
4 to 6.
Yes,
4
Val.
million to 6 million.
4 to 6 million is correct. Good. So let's compare that with white blood cells. So white blood cells are much less numerous. There are not 4 to 6 million. There are 4 to 11,000, which is still a large number per cubic millimeter, but not 4 to 6 million. In terms of shape, they are just a regular spherical shape or round shape. They are larger, and they do have a nucleus, so they're nucleated. And while red blood cells have the job of carrying oxygen around the bloodstream, white blood cells have a role in fighting infection and immunity. Question, yeah.
Is it bad if someone were to have an overexceeding amount of white blood cells?
So the question is, would it be bad if someone had an exceeding amount of white blood cells? We'll get to that. The answer is yes, it would be bad. But we will get to that in a few slides. 2. So, as we mentioned on that big diagram with the test tubes on them, there are types of white blood cells called granulocytes or granular leukocytes, and I'll write that down as well. So granulocytes are also called granular leukocytes because a leukocyte is a white blood cell. And there are three types of granular leukocytes or granulocytes. They are neutrophils, basophils, and eosinophils or eosinophils. I'll give you a little bit of time there to copy those down before I explain them. Sorry, folks, there was a question here in class about vaccines and how your body, your white blood cells recognize things in the vaccine so that they can form an immune response. And I explained that. I do want to mention, I listened to, at the recommendation of my physiotherapist yesterday, a podcast, and you do not have to listen to it unless you do have further interest in vaccines for COVID, how way back in November, there was apparently a paper that came out stating that masks don't work, which people just bought into because they read the Twitter headline. But when people actually read the article, they said they noticed, oh, people are getting the wrong info. Masks don't work when they're not worn properly. Like if you like for example, obviously Fallon right now is drinking water, but if she just wore it like that on her chin, that's not proper wearing of a mask. So anyway, there's a lot of debunking. It was covering something called epidemiology, which is the focus of or the study of infectious diseases and spread of that across the world, like dangerous infectious diseases, as well as infodemiology, which is the spread of information, both true and false, around the world as well. So if you are interested in checking it out, it's about an hour. You don't have to sit down and listen to it all at once, but it's very interesting. It does give a lot of clear info for that. So it's called The Ologies, and they call it The Ologies because they cover different topics each podcast. So this was epidemiology, infodemiology, and sometimes they do psychology or whatever, radiology. So this episode of a podcast, if you have Spotify or Apple Music, it's called Vaccine Infodemiology. And it gives a lot of info because there, as you probably know, there's a lot of info out there. And there's also something that a lot of us are feeling every now and then, or maybe you've already felt it a while ago, called pandemic fatigue, where you're just sort of like tired, sick and tired of everything. And you're just like, well, what's the point? And it's very normal to do that. So if that's something that interests you, it's called The Ologies and Vaccine Infodemiology. I finished listening to it last night. It was great. And it's basically an interview with somebody who has their master's in epidemiology, who spent like the last 10 years learning about infectious diseases. And, you know, they know more about this stuff than we do, than the average person who is not an epidemiologist. Yes. Okay. Continuing onwards now, from granulocytes, There's neutrophils, basophils, and eosinophils. Neutrophils are the most abundant white blood cell, and they're phagocytic. So they come into contact with a pathogen. A pathogen is like a virus or a bacteria or something, an allergen, something that your body should not have inside it. So a neutrophil will come into contact with it and then go through phagocytosis and take it in and eat it. Basophils stain blue and release histamine in relation to like an allergic reaction, like if you have seasonal allergies. And lastly, eosinophils stain red, and they phagocytize allergens. So things like pollen, they'll take those in and so that they're not causing irritation all around your body. And then there are agranulocytes, also known as agranular leukocytes. Remember, these are the ones that don't have those speckles or dots in them. And the two examples of agranulocytes are lymphocytes and monocytes. So these ones are also known as agranular leukocytes, meaning they don't have those granules or grains. Lymphocytes deal with B and T cells, and they play a role in immunity. We'll talk about those later. But those are things that have like memory cells for that. If you encounter something like a vaccine, your body builds up antibodies based on B and T cells having memory. They're also called memory cells. And then there's monocytes, which are the largest white blood cells, and they're phagocytic. All right, everybody have those? What's the commonality in the names of the granulocytes here, folks? Yes. They all end with Phils. So all of these ones here all end with Phils. And then the agranulocytes, these one end with sites. So one thing to keep in mind there. Okay, moving on. This image is super cool. This is a macrophage, which is a type of white blood cell, and it is literally shooting out cytoplasmic extensions going like Spider-Man. That's right. It's grabbing them, brings them into or close to its surface, and then it phagocytizes those bacteria. And we've talked about phagocytosis as well.
It looks like a horror movie monster too.
It looks like a what? A horror movie monster. Yes, it's super cool. And that keeps you healthy for the most part.
Oh, venom.
All right. The next slide is what I told Jack earlier about, what we'll talk about, disorders or diseases with white blood cells. So an increase or a decrease in white blood cell numbers can, not always will, but can indicate a disease. So there's something called infectious mononucleosis caused by Epstein-Barr virus, which sometimes is just called mono. How's it going, Mrs. Dewick?
Pretty good, how are you?
I'm good. Have you heard of mono before?
I have.
Mono is also known as, anybody know?
A kissing disease.
The kissing disease. So it's often passed on from kissing. Okay, so that's mono. And that is due to an increased number of B lymphocytes or B cells. You may have heard of AIDS before as well. AIDS is caused by HIV, which is a human immunodeficiency virus, which basically is a decreased number of T lymphocytes or T cells. AIDS itself stands for acquired immunodeficiency syndrome, and it's a syndrome that you acquire caused by HIV, a virus. So what it does, because it has a decreased number of T lymphocytes, it affects your body's ability to actually defend itself. And something as dangerous as something as simple as a cold or a flu could have a really dangerous effects if you have AIDS, because you don't have the T lymphocytes to protect you. So it could be very dangerous. Leukemia, you may have heard of. Remember, leukocytes are white blood cells. So leukemia is a form of cancer related to white blood cells. And I don't want to be overly simplistic about this, but essentially there's an uncontrolled number of white blood cells. And as you know from today, white blood cells protect your body by attacking any pathogens. So again, attacking any allergens, viruses, bacteria. But if you have an uncontrolled number of white blood cells just growing, they're proliferating or they're being created in large numbers, that's very dangerous, because the white blood cells can then turn and start attacking your body. That's when it becomes really dangerous. Yeah. In terms of white blood cell lifespan, remember, red blood cells live for how long? 120 days. There are different lengths of time for a white blood cell. It can range from a few days for the ones that are on the front lines fighting off pathogens, combating them. And then some live as long as months or even years. So we're talking about 4 months versus years. It's true. Okay, everybody has their stuff there. We'll move on to platelets. So platelets are also known as thrombocytes. And they are like broken down pieces of large cells. And those large cells, I like to say with a big booming loud voice, are called megakaryocytes, because that's a large word, megakaryocytes. 6 syllables yet again. In terms of number, they are much more numerous than white blood cells, but much less numerous than red blood cells. So they're right in the middle there, 150,000 to 300,000. And essentially what platelets are good for is to help with clotting your blood in case you have a cut. Okay. The last thing that we're going to cover over the next 2 and a bit slides, no, next 3 slides, is a very important concept, and that is blood clotting. So we're going to relate to platelets here, and how does your body react when you injure yourself and have a cut, like a serious cut? Or actually, it could even be a small cut. So the first thing that happens is that platelets, let's go back. Platelets will form what we call a platelet plug for immediate stoppage of bleeding. So it's got all these little broken down pieces of those megakaryocytes, and they get sent to the area to try and form like a plug, stop the bleeding. It's like throwing a Band-Aid on it, but an inside Band-Aid. There's going to be a lot of words here that have the part of the word called thrombus in there. So a thrombus is also known as a blood clot. So we're trying to create a blood clot here. So vessels, your blood vessels around the cut area, let's say you grab a knife in the sink and you close your hand on it and you cut your palm. Your blood vessels will then release something called prothrombin activator, and the injured tissues in that area, like your skin and area, will release something called thromboplastin. Prothrombin activator, what do you think that does as a job? Maya? It's in its name, by the way. Prothrombin activator will, it'll activate prothrombin. So prothrombin activator will activate thrombin. What does that do? We'll talk about that in the next few slides, or a few lines. Injured tissues will release thromboplastin. Thromboplastin is kind of like plaster, kind of sticky, and helps with the clot. All right. Sorry? No. Thromboplastin will then stimulate further release of prothrombin activator. So our job essentially is to activate prothrombin. What does that mean? Well, that whole system it requires calcium, but prothrombin activator, here's where it gets confusing, activates the plasma protein prothrombin and turns it into thrombin. So prothrombin is kind of like like before it becomes thrombin, and prothrombin activator turns prothrombin to thrombin. Well, I've said thrombin a lot there. But that's not it, because thrombin also has a job, and it turns fibrinogen, which we talked about under plasma notes today, turns fibrinogen into fibrin. And fibrin forms a clot because fibrin is basically a whole bunch of threads like fibers that will create a meshwork and form a better clot so that you're not constantly bleeding. So I'm going to read that over really quickly so you understand it. You cut your finger, you cut your hand or your finger or whatever, you get a gash, and platelets go right to the area to form a plug to stop bleeding immediately. But that platelet plug won't last forever. So we need prothrombin activator and thromboplastin in the area. Thromboplastin has a job of creating more prothrombin activator. Prothrombin activator activates prothrombin and turns it into thrombin. Thrombin will then turn fibrinogen into fibrin, which are those little fibers that creates a meshwork part of the clot. Question?
So, like, say if you get a paper cut, right, and like there's no bleeding, like for a little bit, and then it starts bleeding. That's because something's trying to protect it.
Yeah, exactly. All right, I'm going to clear my drawings and go to the next slide. Jack, you have a question?
Yes, yes. So, say, like, right, you have a cut in your hand, starts bleeding, and it causes a clot, right? The clot then goes away, and you have a scar. And what if you were to hit the same place where the scar covered the wound, technically? Will that hurt more than original muscle tissue, or
Good question. I don't know.
you don't?
I don't know. It's a good question, though. Okay, blood clotting. This slide, you do not need to know. I will not ask you to label this on a diagram. But for those of you who are better at learning through, where's my cursor? I can't even find it. Oh, there it is. Better at following more visual things. Basically, it says here, damaged tissues and cells release thromboplastin. Platelets form a platelet plug. You then get prothrombin activator, which turns prothrombin into thrombin. Thrombin will then form or change fibrinogen into fibrin. And you can see all of these little threads here on the image on the right. And those are fibrin threads that basically trap red blood cells and other cells in there and form a nice plug. It's sort of like gauze or a meshwork that stops blood flow. So that's essentially what happens to create a clot. We're on to our last slide for today, which says, as I had mentioned, the clot is composed of a network of fibrin threads and trapped cells. And eventually, as your damage heals, you have another plasma protein called plasmin that breaks down the clot. So it's like, okay, we're healing. We need to get rid of some of the scab, the wound, and bring it back to normal. Little point of interest, if your blood is allowed to clot in a test tube, it forms what's called a serum. And a serum is basically plasma without fibrinogen. So it has the inability to turn into fibrin, and then it cannot create a clot. Last little point here, there's something called hemophilia, and that is the inability for your blood to clot properly. So it has a real tough time to do that. So it's a clotting disorder. It's very prevalent in the royal family in England. It dates all the way back to Russian descendancy there, and it's a very famous sort of genealogy or inheritance pattern that's covered in grade 12 biology. Essentially, it's a deficiency of a clotting factor where small injuries, like if you grabbed a knife accidentally, that could be really like fatal because your body won't be able to stop the bleeding. It won't be able to clot, so then you just bleed to death and become fatal. So that's hemophilia. The last slide that you have, you don't need to pay much attention to that. That's this one. It basically shows the difference between blood, plasma, and serum right here. That's important to know, but I'm not going to ask you to fill this out. You don't need to know tissue fluid right now or lymph. We will talk about this one when we get to the immune system. That's all for today, folks at home. You can feel free to leave the meeting, and we'll see you tomorrow.